Among the many iconic dinosaurs of the late Cretaceous, few inspire as much discussion regarding predator-prey dynamics as the relationship between Tyrannosaurus Rex and Ankylosaurus. While T.rex is often imagined as the undisputed apex predator of its environment, fossil evidence and biomechanical studies consistently highlight one species that even this formidable carnivore would have treated with exceptional caution. Ankylosaurus magniventris possessed a combination of defensive adaptations that placed it in a category entirely its own, creating an animal that was not only difficult to kill but also capable of inflicting fatal injuries even on the largest predators of its time. This species represents one of the most extreme examples of evolutionary specialization, with an anatomy focused almost entirely on protection and counterattack. Its heavily armored body, low center of gravity, and immense tail club made it structurally distinct from other herbivores within the Hell Creek ecosystem. These features did not evolve randomly. Instead, each trait reflects millions of years of selection pressure in an environment containing some of the most dangerous theropods in Earth's history. Understanding Ankylosaurus therefore provides critical insight into why T.rex approached this species differently from other prey, recognizing that even a minor miscalculation could result in catastrophic injury. The scientific recognition of Ankylosaurus began in 1906 when the renowned paleontologist Barnum Brown uncovered fragmentary remains in the Hell Creek Formation of Montana. These fossils included sections of armor, vertebrae, and limb elements, offering the first substantial evidence of a heavily armored dinosaur far larger than previously identified ankylosaurids. Brown named the species Ankylosaurus magniventris in 1908, with the genus meaning fused lizard, a reference to the animal's extensively ossified skeletal structure. The specific name, magniventris, meaning great belly, alludes to the species' unusually broad body cavity, which later research suggested played significant roles in digestion and stability. Although initial discoveries were incomplete, they provided enough diagnostic material to distinguish Ankylosaurus from other armored dinosaurs found earlier in North America. Subsequent expeditions uncovered additional osteoderms, tail club elements, and skull fragments, gradually refining scientific understanding of its anatomy. Despite continued efforts, Ankylosaurus remains known from surprisingly limited fossil material, contributing to ongoing debates regarding its maximum size, armor arrangement, and behavioral adaptations. The rarity of remains adds to the species' mystique, reinforcing the idea that this animal occupied a unique ecological role and prompting continued interest in understanding why even large predators such as T.rex interacted with it so cautiously. Ankylosaurus belongs to the family Ankylosauridae, a clade of herbivorous dinosaurs characterized by low-slung bodies, extensive dermal armor, and specialized defensive adaptations. Within this group, Ankylosaurus represents one of the latest and most derived members, appearing shortly before the end Cretaceous extinction event. Its closest relatives include species such as Anodontosaurus, Euplocephalus, and Zil, all of which exhibit varying degrees of cranial ornamentation, armor complexity, and tail club morphology. Ankylosaurus, however, stands apart due to its exceptional size and the unique configuration of its osteoderms, which suggest a higher degree of defensive specialization than that seen in earlier forms. Phylogenetic studies place the genus firmly within the Ankylosauridae subfamily, a group distinguished by tail clubs supported by modified vertebrae and reinforced tendons. The evolutionary pathway leading to Ankylosaurus indicates a gradual enhancement of protective structures over millions of years, reflecting ongoing interactions with large carnivores. While classification debates continue due to incomplete fossil material, most analyses agree that Ankylosaurus exemplifies the peak of ankylosaurid armor evolution. Its placement within this lineage helps clarify not only its physical characteristics but also the ecological pressures that shaped its development, offering important context for understanding why it posed an unusual threat to apex theropods such as T.rex. Among armored dinosaurs, Ankylosaurus holds the distinction of being the largest known member of its group. Estimates suggest a length of approximately 6 to 8 meters, with some projections reaching up to 9 meters based on scaling from close relatives. Its mass is generally placed between 6 and 8 metric tons, although certain reconstructions propose even greater weights depending on muscle distribution and armor thickness. The animal's body plan was remarkably broad, with a barrel-shaped torso supported by robust limbs positioned widely apart to maintain balance under significant load. The skull, though proportionally small relative to body size, was heavily reinforced and low to the ground, contributing to the species' stability and defensive posture. Such dimensions indicate an animal that relied not on speed or maneuverability but on structural resilience. The overall size of Ankylosaurus, combined with its extensive dermal armor, would have presented a formidable obstacle for predators. Even a fully mature T.rex would have needed to exert considerable force to penetrate its defenses, and doing so risked encountering the animal's powerful tail club. This combination of mass and protective features made Ankylosaurus one of the most physically imposing herbivores of its ecosystem, reinforcing its status as a species that large carnivores approached with considerable caution. The exceptional weight of Ankylosaurus derived from several interrelated anatomical features designed to maximize defensive capability. A substantial portion of its mass came from the presence of osteoderms, large, fused plates of bone embedded within the skin. These structures contributed significant density, particularly across the back, hips, and flanks, where protection was most essential. Additionally, the ribs were unusually wide and strongly curved, expanding the torso and increasing internal volume for complex digestive organs. The vertebrae and limb bones were extremely robust, built to support both the armor and the broad musculature necessary for stability. These skeletal features alone would have resulted in a heavy animal, but the musculature required to operate such a body plan further increased weight. Tail muscles in particular were exceptionally developed, enabling the animal to wield its club effectively. The overall distribution of mass created a low center of gravity, making it difficult for predators to overturn the animal even with considerable force. While its weight limited mobility and speed, it simultaneously enhanced its resistance to predatory attacks. This trade-off reflects a defensive evolution highly refined for survival in an ecosystem dominated by large theropods capable of delivering powerful bites. The armor of Ankylosaurus represents one of the most advanced defensive systems in dinosaur evolution. Its dorsal surface was covered with interlocking osteoderms of varying shapes and sizes, forming a near-continuous shield capable of absorbing significant impact. Many of these osteoderms possessed intricate internal structures of dense bone interspersed with vascular channels, suggesting active maintenance and possibly growth throughout the animal's life. The arrangement of these plates provided overlapping protection while maintaining some degree of flexibility, allowing the animal to shift its weight, turn, and position itself in response to threats. Regions most vulnerable to predatory attack, such as the neck and shoulders, were reinforced with particularly large and thick elements. The skin surrounding the osteoderms was likely keratinized, offering an additional protective layer. This complex armor system did more than simply shield the animal. It also increased the difficulty predators faced in locating weak points. Even a powerful bite from T.rex would have struggled to penetrate fully through these layers, and doing so would have required precise targeting of less protected regions. This level of defense contributed significantly to the species' reputation as one of the few animals capable of discouraging attacks from the most formidable carnivores of the late Cretaceous. Compared with earlier ankylosaurids, Ankylosaurus displayed several distinctive armor characteristics that indicate a more extreme level of specialization. Many ankylosaurs possess rows of osteoderms arranged in relatively predictable patterns. However, the osteoderms of Ankylosaurus were unusually large, variably shaped, and more deeply embedded within thick layers of soft tissue. This arrangement created a mosaic-like surface rather than the uniform linings seen in species such as Euplocephalus or Anodontosaurus. Additionally, Ankylosaurus featured a uniquely broad spacing between osteoderms across the torso, suggesting that the surrounding keratin sheaths may have been more extensive than those of its relatives. Some paleontologists propose that the animal's size allowed for heavier plates without compromising mobility, resulting in armor that was simultaneously more massive and structurally integrated. Cranial armor was also especially reinforced, with fused bones along the skull roof forming a rigid protective shield. Although other ankylosaurids exhibited cranial ornamentation, none achieved the same degree of fusion and thickness observed in Ankylosaurus specimens. These differences point toward selective pressures that intensified late in the Cretaceous, likely due to interactions with large theropods. As a result, Ankylosaurus developed an armor configuration optimized to withstand extreme bite forces while maintaining enough flexibility to enable precise tail club use. The question of whether Ankylosaurus could be considered bulletproof often arises from modern reconstructions that highlight the immense thickness and density of its osteoderms. While the term is metaphorical, biomechanical analyses indicate that its armor could withstand impacts far greater than those encountered by most other dinosaurs. Individual osteoderms, some measuring over 50 centimeters across, were composed of compact bone with complex internal reinforcement, enabling them to dissipate force across broad areas. If a modern projectile were scaled to comparable energies of a t.rex bite, the osteoderms would likely prevent penetration, although secondary fractures and soft tissue damage could still occur. Importantly, the keratinous layer overlaying the osteoderms may have further increased resistance by distributing force more evenly. Even so, describing Ankylosaurus as truly bulletproof oversimplifies the nuance of biological armor. Certain areas, such as the limbs, underbelly, and joints, remained vulnerable, and a sufficiently well-placed bite from a large theropod could exploit these openings. Nonetheless, within the context of its ecosystem, Ankylosaurus possessed defensive capabilities equivalent to a near-impenetrable shield. Its evolutionary design was not to repel literal projectiles but to endure and counter the most powerful crushing forces produced by predators of the late Cretaceous. The tail club of Ankylosaurus was a biomechanical structure capable of generating tremendous force. Studies examining the morphology of the vertebrae and ossified tendons show that the tail's posterior half functioned as a rigid lever, while massive muscles at the base provided the torque necessary for powerful lateral swings. Unlike many dinosaurs, Ankylosaurus invested considerable energy into developing musculature specifically for tail movement, suggesting that the clubs served as an essential defensive tool. Biomechanical modeling estimates that a fully grown Ankylosaurus could strike with forces exceeding several thousand newtons, comparable to the impact of a sledgehammer wielded with exceptional strength. The club's mass alone contributed significantly to its destructive power. Fossil evidence indicates that some clubs weighed well over 20 kilograms. Such mass, combined with rapid acceleration, created a weapon capable of fracturing bone, including the legs or ribs of large predators. The design allowed for repeated strikes, although each swing required the animal to stabilize its body and shift its weight. This capability placed Ankylosaurus in a rare category of herbivores that could deliver active, disabling counterattacks. For an apex predator like t.rex, even a single blow from this structure could result in severe or fatal injury, influencing predatory behavior accordingly. Ankylosaurus employed its tail club not as a primary method of hunting or aggression, but as a highly strategic defensive instrument. When threatened, the animal likely adopted a stance that maximized stability, lowering its body and orienting its armor toward the predator. From this position, the tail could be swung laterally with precision, targeting the legs or lower torso of an approaching theropod. Fossil evidence from related ankylosaurids shows impact damage on both predator bones and ankylosaurid osteoderms, supporting the idea that tail strikes were effective and commonly used in encounters. The weapon's range of motion was optimized for sweeping arcs rather than vertical strikes, allowing Ankylosaurus to defend a broad perimeter around its body. Its low center of gravity made it difficult for predators to push it off balance, enabling repeated defensive motions. The club's effectiveness did not rely solely on raw force. Its structure allowed it to deliver force at specific angles that maximized damage. Ankylosaurus did not need to injure a predator severely to deter an attack. Disrupting a leg or causing acute pain would often be sufficient. Over evolutionary time, these defensive interactions helped refine the species' tail architecture, making it one of the most formidable passive weapons in its ecosystem. Juvenile Ankylosaurus individuals lacked many of the defining traits that made adults so resilient. Their osteoderms were smaller, more widely spaced, and less mineralized, offering only limited protection compared to the heavily armored adults. Furthermore, the tail club, an essential defensive structure, was absent or only minimally developed in young individuals, leaving them without the primary weapon that deterred large predators. The overall body mass of juveniles was significantly lower, making them more vulnerable to overturning or being subdued by predators such as the Dakotaraptor or juvenile t.rex. Their limited size also meant they had fewer internal reserves to sustain injuries or prolonged chases. Additionally, the digestive system, while functional, was not yet adapted for the high-volume processing seen in adult individuals, requiring juveniles to forage more frequently and in less secure environments. The combination of these factors likely resulted in a high mortality rate among young Ankylosaurus. Many would not survive long enough to reach the heavily armored adult stage, contributing to the species' rarity in the fossil record. These vulnerabilities underscore the dramatic transformation Ankylosaurus underwent throughout its development, transitioning from a relatively exposed juvenile into one of the most impervious herbivores of the late Cretaceous. Unlike many herbivorous dinosaurs of its time, Ankylosaurus does not display strong evidence for living in large social groups. Fossil beds containing multiple individuals of the same species, common among hadrosaurs and ceratopsians, are virtually absent for Ankylosaurus. Instead, most Ankylosaurus remains are discovered as isolated specimens, suggesting that adults were predominantly solitary. This does not mean the species lacked all social structure. Juveniles may have formed temporary groupings for increased protection, but these associations likely diminished as the animals grew larger and their armor became fully functional. Adults, equipped with nearly impenetrable defenses and powerful tail clubs, had little evolutionary incentive to rely on herd safety. Their foraging behavior, focused on low-lying vegetation, likely also reduced the need for cooperative feeding. The habitats Ankylosaurus occupied, dense forests and floodplains, may have further encouraged a solitary lifestyle by restricting visibility and movement. Although some paleontologists have proposed seasonal aggregations, there is currently insufficient evidence to support this. The prevailing interpretation is that Ankylosaurus led mostly independent lives, interacting with others of its species primarily during mating periods or territorial encounters. This solitary behavior differentiates it from many prominent herbivores in Hell Creek and contributes to its relatively sparse appearance within the fossil record. Ankylosaurus was a strict herbivore that relied on abundant ground-level vegetation for sustenance. Its broad muzzle, low-slung body, and strong beak suggest that it fed predominantly on ferns, cycads, club mosses, and a variety of low shrubs. These plant types, while plentiful, were not particularly high in nutrients or caloric density, meaning that the animal needed to consume large amounts to meet its daily energy requirements. Estimates suggest that a fully grown Ankylosaurus may have needed to ingest around 60 kilograms of plant material per day, an amount comparable to that eaten by modern elephants. This high intake was facilitated by its efficient digestive system, which likely utilized hindgut fermentation to break down tough plant fibers. As a result, Ankylosaurus could extract nutrients from vegetation that would have been largely indigestible to many other herbivores. The species' large body size further helped regulate energy use, allowing it to process foods slowly and maintain a relatively low metabolism for such a massive animal. Its feeding strategy was well suited to the lush environments of the late Cretaceous, where abundant underbrush provided a continuous supply of the plant matter it depended on. This dietary specialization played a significant role in shaping its anatomy and behavior. Although Ankylosaurus was a herbivore, its teeth differed from the broad, grinding dentition commonly associated with large plant-eating dinosaurs. Instead, the species possessed small, leaf-shaped teeth with distinct cusps and sharp edges designed for slicing rather than crushing vegetation. These unusual teeth allowed Ankylosaurus to shear leaves into manageable fragments before swallowing them, minimizing the need for extensive oral processing. The beak at the front of its jaws played an equally important role, stripping foliage from stems with considerable efficiency. Taken together, this combination of a narrow keratinous beak and sharp cutting teeth suggests a feeding strategy focused on precision and selective browsing. The animal did not rely on mastication to the degree seen in hadrosaurs, which possessed complex dental batteries for grinding plant material. Instead, Ankylosaurus transferred the bulk of its digestive workload to its expansive gut, where microbial fermentation completed the breakdown of tough plant fibers. The structure of its teeth also reveals clues about its evolutionary lineage, reflecting adaptations inherited from early ankylosaurids, while showing modifications unique to the genus. Their sharpness and serrated edges were particularly well suited to the dense understory vegetation prevalent in the ecosystems it inhabited. One of the most recognizable features of Ankylosaurus is its extremely broad midsection, which gave the animal a distinctive barrel-shaped profile. This expanded abdominal cavity housed the extensive digestive system necessary for processing its fibrous plant diet through hindgut fermentation. Fermentation requires significant internal space to accommodate large chambers, analogous to fermentation vats, filled with symbiotic bacteria that break down cellulose. The wider belly not only provided room for these digestive chambers but also supported prolonged retention times, allowing the animal to extract the maximum possible nutrients from low-quality vegetation. Additionally, the broad body contributed to overall stability, lowering the center of gravity and making it more difficult for predators to overturn the animal, a tactic that might otherwise bypass its dorsal armor. The shape of the ribcage reflects this adaptation, with ribs that flare outward more dramatically than those of most other dinosaurs. This robust structural design also provided a strong foundation for supporting the heavy armor and massive musculature associated with the tail club. Consequently, its wide belly was not merely a dietary adaptation but a multifaceted anatomical feature that enhanced digestion, stability, and defense simultaneously. Ankylosaurus possessed sensory capabilities that, while not exceptional in all areas, were well adapted to its environment and lifestyle. The most prominent sense appears to have been smell. The nasal passages of Ankylosaurus were unusually complex and elongated, possibly functioning as both a respiratory filter and an olfactory enhancer. This intricate system, combined with a relatively large olfactory bulb, suggests that the animal relied heavily on scent to detect food sources, identify individuals, and monitor its surroundings for potential threats. In contrast, its vision was likely less refined. Although it possessed binocular sight due to forward-oriented eyes, the optical acuity of Ankylosaurus seems to have been limited compared to that of predatory species. Its eyesight was probably sufficient for navigating its forested habitats and recognizing nearby movement but not for detecting distant objects. This reliance on smell over sight fits well with its ecological role as a slow-moving ground browser. The combination of robust olfactory senses and adequate vision allowed Ankylosaurus to function effectively within dense vegetation, where scent-based cues were more reliable than long-range visual detection. This sensory profile reflects a lifestyle in which environmental awareness was essential but did not require the keen vision associated with active predators. And when we look closely at the vegetation that dominated its ecosystem, we begin to understand why this animal reached such extraordinary levels of mass and defensive specialization, because the landscape it occupied was not some barren, windswept plain where food was scarce, but rather a warm, humid, plant-rich environment dominated by dense understory ferns, broad-leafed angiosperms, sprawling ground-level growth, and seasonal bursts of soft, nutritious foliage that allowed herbivores to consume vast quantities with relatively little competition, and in this nutrient-heavy backdrop, the animal that t.rex respected most could maintain a foraging lifestyle that required almost continuous feeding. And unlike the towering sauropods that specialized in high browsing or the ceratopsians that engaged in intense seasonal migrations, this creature thrived in heavily vegetated floodplains, river deltas, and forest edge habitats where new plant growth was constantly regenerating after periodic flooding events, offering an effectively renewable food supply. The stability of this ecosystem meant that an herbivore with substantial body mass could remain relatively sedentary while still consuming enough vegetation to maintain its enormous size, and it also meant that predators such as t.rex frequently encountered these armored tanks during their daily movements, creating an environment where both hunter and potential prey knew exactly what the other was capable of. And when we examine the broader climatic patterns of the region, we see a late Cretaceous world defined by warm temperatures, high humidity, and pronounced wet-dry seasonal cycles that produced alternating periods of dense vegetation growth and slower, more nutrient-limited intervals, and within this fluctuating cycle, our heavily armored dinosaur developed metabolic and behavioral strategies that allowed it to maintain a stable nutritional intake even during periods when plant regrowth slowed. These climatic shifts also influenced predator behavior, because large theropods like t.rex adjusted their activity patterns to coincide with seasonal prey concentrations around water sources and vegetated floodplains, which inevitably increased the frequency of encounters between the apex hunter and the one herbivore it learned not to underestimate. The relatively frost-free environment and the absence of significant cold seasons meant that this creature did not experience the energetic stress common in animals living closer to the poles, enabling it to devote more biological resources to armor maintenance, tail club strengthening, and overall muscle density, all of which contributed to the traits that made t.rex approach it with notable caution. Thus, the climate did not merely shape the plants and animals of the region, it indirectly shaped the entire predator-prey dynamic. And one of the most persistent questions surrounding this dinosaur is why such a formidable, well-adapted, and ecologically successful herbivore appears so rarely in the fossil record, because despite its size, despite its armor, and despite its geographic range, the remains we have are surprisingly scarce, leading to ongoing discussion about whether this reflects actual biological rarity or a deeply skewed preservation bias. Many paleontologists lean toward the latter explanation, noting that its heavily forested, floodplain habitats were environments where buried remains often decayed before they could fossilize, where river activity scattered bones over wide areas, and where scavengers disrupted carcasses quickly. Others propose that its population densities were simply lower than those of ceratopsians or hadrosaurs, not because it was unsuccessful, but because its enormous bulk and constant feeding needs meant that only a limited number of individuals could be supported within any given region. And although this rarity complicates our understanding, the few specimens we do possess are remarkably informative, giving us enough anatomical data to confidently reconstruct its size, armor, tail mechanics, and ecological role, and enough behavioral implications to understand exactly why even the apex predator of the Cretaceous approached it with respect. And when we place all of this information together, the armor, the tail mechanics, the feeding strategies, the environmental pressures, and the predator-prey dynamics, we see a creature that occupied a highly specialized niche, one where its biology formed a complete defensive system rather than a collection of isolated traits. And this integrated design meant that any predator considering an attack needed to weigh the enormous potential cost against the uncertain reward. In ecosystems where energy balance was everything, t.rex could not afford unnecessary injuries, because even a single fractured toe or a deep tissue wound could compromise its hunting capacity for weeks, and few animals in its environment posed a more serious defensive threat than this single armored herbivore. Its weaponry was not merely deterrence. It was a biomechanical hazard capable of ending a predator's career in one miscalculated strike. And so, in the grand tapestry of late Cretaceous life, this dinosaur gained a reputation not by speed or aggression, but by reliability. Reliability in defense, reliability in survivability, and reliability in making even the apex predator think twice before engaging. It was not the largest herbivore, nor the fastest, nor the rarest, but it was, by every biological metric we can measure, the only dinosaur t.rex genuinely feared, and when we step back from all the anatomical details, environmental context, biomechanical measurements, and ecological comparisons, what becomes clear is that this dinosaur earned its reputation not through myth-making or exaggeration, but through the consistent, testable evidence that shows how thoroughly its body was engineered to make predation an energetically unwise decision for even the most capable carnivore of its time. Its armor was not decorative, its tail club was not a secondary feature, and its immense body mass was not simply a byproduct of herbivory. Each trait contributed to a unified defensive framework that transformed it into something no predator wanted to challenge without absolute necessity. And in an ecosystem where survival depended on minimizing injury and maximizing efficiency, t.rex, for all its power and predatory dominance, behaved exactly as any intelligent apex hunter would. It recognized risk, evaluated cost, and avoided confrontations that could jeopardize its role at the top of the food chain. That is why, among all the dinosaurs living alongside it, this species stands apart, not as the biggest, not as the most aggressive, but as the one animal whose defenses were so thoroughly optimized that even the apex predator approached it with caution. And in understanding that dynamic, we gain not only insight into their biology, but also a clearer picture of the remarkably complex ecosystems of the late Cretaceous, where fear, respect, and survival were interwoven into the very structure of life.